All right, so we're talking about ethers. We're talking about this functional group. It's got an oxygen motif, and it's the oxygen sandwiched between two R groups. We've already talked about naming them, naming crown ethers, and we talked about naming thiols and naming thiol substituents, which are mercaptos. So if going in order of the textbook spends some time talking about crown ethers and the chemistry of crown ethers. Now, we talked a little bit already about naming them. And so we know that this one is named based on the number of total atoms in the chain and the number of oxygens. So there's 1, 2, 3, 4, 5, 6 oxygens. So this is a crown, and then it has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons, plus the 6 oxygens. So this is 18 crown 6. Now, the reason that the textbook spends time on crown ethers is because there was actually a Nobel Prize awarded for work on these types of ethers. They're not so hot anymore when it comes to research, but it is still important from a synthetic point of view. We already know that ethers can stabilize negative charge or positive charges. And in fact, we know that in order to do Grignard, we must actually do that in the presence of diethyl ether. And the reason is that the ethers are what actually stabilize the Grignard reagent. And the Grignard reagent can't be prepared without diethyl ether. And the same thing happens with crown ethers. It just happens a little bit more aggressively. There's obviously a lot more lone pairs. And so what you end up with is a cavity here. And this cavity is able to solubilize even in non-polar systems. So for instance, if we take something like this, and we take potassium fluoride, and we put it in benzene, potassium fluoride will not dissolve in benzene. It's a salt, and benzene is essentially a non-polar solvent. We can't use a polar solvent because fluoride then reacts too aggressively with it. I know that we've talked about not being able to use fluoride. But if I then take and mix in benzene this ether, 18 crown 6, what happens is the potassium becomes solvated. If the potassium is solvated, well, then the fluoride is available as a nucleophile to do regular old SN2 style reactions. And so what you guys have to know is about these crown ethers are what they solubilize. And now I'm going to leave 18 crown 6 up here in the corner, but I want to just go ahead and show other ones. So we could have 1, 2, 3, 4, 5 oxygens. They're always going to be connected with a 2-carbon chain. So that's crown 5. And then how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 5. 15 crown 5. And 15 crown 5 will solubilize a sodium ion. And so think about the periodic table and where these things appear in the periodic table. Sodium is smaller than potassium. Potassium is larger than sodium. So it takes a larger crown to solubilize that cation. And we can do the same thing with the 4 oxygen crown ether. We can solubilize the lithium, and that's 12 crown 4. So again, in summary, what crown ethers are good at doing is solubilizing and interacting with metal ions. they do this so well that it will work even in nonpolar environments that would leave other anions available to do nucleophilic attack. This even works for potassium permanganate, KMnO4. We can use 18 crown 6 to solubilize potassium permanganate and have the manganate ion be able to do oxidation in a nonpolar environment. And so what you guys have to be able to do or think about, I'm going to keep this at the corner, is to think about these reactions. And so I'm going to write this one down. I'm going to use a Y. And you have to do AX, where it happens in a substitution reaction in benzene with some sort of crown ether. And this is, and what you have to remember is this, is that if A equals potassium ion, then the crown is 18 crown 6. If the ion equals sodium ion, then it's 15 crown 5. And if the ion is the lithium ion, then it's 12 crown 4. And so you list where I've got crown ether in this red black box, you would actually list the particular crown. And so what I might do is something like, and the only other reaction that you have to think of is this. If I have potassium permanganate in benzene, we know that we would need 18 crown 6 for this. This is actually going to do oxidation and create a diol, just like potassium permanganate would do in a reaction with that we learned last semester. And I think that would be a 2-step reaction with sodium borohydride in cold environment. Okay. Any questions about that? I want to make sure that this is what these are. So again, it's hard with not having an actual reaction board. So are there any questions? Any questions? All right, so your goal is to be able to, I know it's hard not having a reaction board, but these particular reactions would be on the reaction board. Questions going once. Questions going twice. Okay. Out into the ether. All right, so as it goes with these chapters, what we're going to do is we're going to talk about the physical properties, then the reactions that produce ethers, and then the reactions of ethers. Now, for this particular chapter, we're going to do light treatment of the physical properties. We'll talk about it in just a second, but at the end of the day, ethers are slightly polar, but they don't have hydrogen bonding, and so their boiling points are similar to nonpolar compounds. We'll then talk about reactions that create ethers, with the most important reaction being the Williamson Ether Synthesis. Then we're going to talk about reactions that of ethers, and ultimately what we're going to talk about is epoxides. And the epoxides are 3-membered rings where one member of the ring is an oxygen, and that's where some interesting chemistry happens, and that's what we're going to focus most of our time on. Then we'll spend a little time talking about sulfides. But let's talk about preparation of ethers just from a basic standpoint. I can take an alcohol and I can react it with an acid. And let's just make it H3O plus for the moment. And what'll happen is that the alcohol will protonate, and I'll have water here. What I can then do is another molecule of the alcohol can now act as a nucleophile and do an SN2 style reaction. That creates the protonated ether. And then water can come along, or anything else in the solution, to deprotonate that. And then I can form the product ether. So that's one of the ways to make an ether. It could be water. It could be another one of the alcohols. Now there's a problem with this. What if I were to, so this is a mechanism that I expect you to know. And so I want to just pause a beat, make sure there's any questions about it. All right, so there's a problem with this. So let's simplify this mechanism and let's make the reaction look like this. So here's a reaction. You might write this one on your reaction board. You can get this, okay? So the question is this: what if I had R prime OH and I mixed it with ROH? What would be the possible outcomes of this reaction? I could have R prime OR. I could have R prime OR prime, or I could have ROR. This is not synthetically practical because there's nothing that really would control which one of these three ethers I would make. And so this isn't a synthetically practical way to make ethers. They're great as long as the ether is symmetrical. This one is symmetrical. Works just fine in that situation. But in the situation of an unsymmetrical ether, it's not too practical. And so what we rely on at that point is the Williamson Ether Synthesis. And the basic reaction for the Williamson Ether Synthesis is that I start out with an alcohol. I react it first with sodium hydride, and then I can react it with an alkyl halide, and that will get me my unsymmetrical ether. So there's the basic reaction. All right, so what's going on here from a mechanistic perspective? Now, you already know this part of the mechanism, and so I'll remind you, how does the hydride work? Well, the hydride is acting as a base, doing a proton transfer, creating the alkoxide and H2 gas. Now, the alkoxide is, at this point, should be recognized as a good nucleophile. And a good nucleophile can do substitution reactions with alkyl halides. And so you already know this part of the reaction as well, SN2. And that's what makes my ROR prime. Okay, so this is the Williamson Ether Synthesis. Here's the reaction. Here's the mechanism. Knowing that it's an SN2 step on the second end after the proton transfer, that means there's going to be some limitations. And so let me show you what I mean by that. What if I want to create this ether? So I've got ethyl here, and I've got tert butyl here. And so that means there was two possibilities. I could have started with the ethyl alcohol and a tertiary alkyl halide, or I could have started with a primary alkyl halide and tertiary butanol. Either one of these reactions could form that ether. Which one of these reactions will actually readily form the ether where the other one won't do so well? So just spend a second thinking about it. And I actually want you to type this into chat. I want you to tell me, is it A or is it B? And then tell me why you think that is real quick. So just think about it for a second. Think about what I said in the mechanism. At least type in chat if you can hear me. Have I just been talking to nobody? Okay, good. We've been spending a long time talking to find out if nobody's here. I'm thinking, all right. Everybody can hear me. Can anybody think about why this is? Why? Okay, Josh says A. Shelly says A. Anna says A. Grace says A. Karen says A. Alexa says A. Everybody says A. And y'all are all... Y'all are all wrong. I appreciate it. Let's think about it though for a second. What Alana says, then it's B. I appreciate that. Right. If it's not A, then it's B. Good job. So let's think about what it actually is going on here. What is the second step of the mechanism? Type that in. That's right. SN2. Keep going. Yes, that's right. SN2. What kind of substrates favor SN2 reactions? Primary substrates, secondary substrates, or tertiary substrates? Just waiting just 1 second. So let's think. If I'm going to do an SN2 reaction, I have a nucleophile, and the nucleophile reacts with a substrate, and it substitutes for whatever the situation is, whatever X is on the substrate, the leaving group. And so the basic SN2 mechanisms involves nucleophilic attack and loss of a leaving group at the same time. Let's take this substrate and let's expand it out a little bit so that we can think about what might be better. Well, here's methyl. It could be methyl. Let me back this up. It could be primary. It could be secondary, or it could be, 1 second, tertiary. Which one of those is favored? People are starting to sort it out now. Yes. Why? What's the reason? Reach into your tool bag and tell me what's the organic chemistry reason why primary is favored over secondary over tertiary. That's right. Exactly. Now I'm starting to see some actual mechanistic moves. One student's talking about the actual transition state requiring backside attack. In order to get that backside attack, I need to eliminate as much steric hindrance as possible. That's right. Primary, then secondary, then tertiary for SN2. The opposite for SN1. Now we're starting to remember back to our Orco 1. Exactly. So let's think now back to the reaction that we're proposing. If I want to do Williamson ether synthesis, and I know that the second step is SN2, where am I going? Which one of these is actually going to provide the less sterically hindered substrate? In other words, we would want the alkyl halide to be less hindered. In the first step, we're going to produce an alkoxide. We're going to produce the nucleophile. I want my substrate to be as less hindered as possible. So the preferred reaction is reaction B. And so at the end of the day, to kind of remind you guys, here's the reaction and the mechanism. Yeah, this is good. I love that feedback. Students are telling me this makes a little bit more sense. At the end of the day, here's the basic reaction from what I would normally include on the reaction board. This is what you have to know. An alcohol, 2 steps, sodium hydride, then some sort of alkyl halide makes you an ether. Here's the mechanism. I'll review this in just a second. Here's the mechanism. And so this is the important part. And I think this will answer this question to explain it again. In the mechanism, in this reaction scheme, we're producing an alkoxide in the first step. The alkoxide then becomes a nucleophile. It's able, with its negative charge, to attack partially positive charges on carbons. If it's going to do this, then it wants to do this in positions that are less sterically hindered. If I create a tertiary substrate, then that alkyl halide has less room to attack that carbon. This increases the energy of the transition state. And if I increase the energy of the transition state, then that reaction is slow compared to one where instead of CH3 groups, I just have hydrogens. And so this is the methyl version, but it's still pretty much favored if only one of those groups is another carbon. And this is the example of a primary substrate. So now that I've created the alkoxide, and in the second step of the reaction, it's going to do an SN2 substitution reaction. Then when it does the SN2 substitution reaction, we want this to have as little hindrance as possible, because we don't want to hinder this SN2 attack. We want that to be as favored as it can be. Does that help? Okay, let's kind of, if we're still confused later, let's meet offline and kind of go through that a little bit. So at the end of the day, you're going to have, so let me sort of put it all together. At the end of the day, you're going to be able to create an ether by using this synthesis, by having an alcohol react with sodium hydride and an alkyl halide, and it's going to create an ether. At the end of the day, R prime should be the least hindered of the two R groups. And this is because the second step, that second step of the reaction, is an SN2 step. And so if that, I want to leave it there. And so if there's still questions with that later on, then what I want to do is I want to address that offline. So let's take a look at one sort of exception to this bit. if I do this with benzene, or excuse me, with phenol, then I actually don't need the hydride to be in other words, hydride is really strong. With benzene, I'm going to have some resonance stabilization in the alkoxide that's formed to form phenoxide. And so I can just use a relatively weak base like sodium hydroxide, but then I still react it with an alkyl halide, and I get this ether. So it's exactly the same mechanism. It's exactly the same result. It's just that I don't need as strong of a base as sodium hydride in the case of phenol because of the resonance stabilization here. So that's just one little addition to that piece. And so let me give you an example. How would I synthesize this with Williamson Ether Synthesis? Remember, I'm going to have two R groups, R and R prime, and we want R prime to be the least hindered. And so let's identify the types of substrates the connections would be making. This one is at a primary substrate, and this one is at a secondary substrate. So identifying it in this way helps me understand which one R prime should be. In other words, which one should be the alkyl halide. In the reaction scheme, I'm saying that the alkyl halide should be the less hindered position. And so now that I've identified the two positions as being primary and secondary, I know how I can go ahead and do this reaction. That means this one was the alkyl halide, and this one must be is it HOL? Oh my goodness. So that means that if I were to show it from the perspective of the alcohol, which is what I should do because that's going to be the first step, then I know that this is my alkyl halide, and that will form the ether that I'm interested in. So I hope that maybe at this point, the explanation, the review, and the problem example sort of helps you see how you deal with this. At the heart, again, at the end of the day, at the heart of the mechanism is an SN2 reaction. And so you have to go back into chapter 7, into that substitution reaction, and think about the differences in the steric hindrance of the substrate when it comes to nucleophilic attack. If we're doing nucleophilic attack at the same time as the loss of a leaving group, then the quickest nucleophilic attack happens at the least substituted location. So to review, we've talked about two different ways to make ethers so far. That's the acid catalyzed hydration of an alcohol when we're dealing with a symmetrical ether. We've talked about Williamson Ether Synthesis, which we can use to create an unsymmetrical ether. And I just want to remind you that this is a reaction that you also know. When I make this nucleophile a water, you get a Markovnikov addition of an alcohol. That's oxymurcuration-demercuration. But I can, instead of doing oxymurcuration-demercuration, I can do alkoxymurcuration-demercuration, and I get essentially the exact same result, but instead I form an ether. And so this is a review of a reaction from the first semester of organic chemistry. And so just a reminder that the oxymercuration-demercuration reaction works just as well with alcohols as it does with water, and you end up doing alkoxymurcuration-demercuration. So it would be the Markovnikov formation of an ether in that case. Okay, so now that we've talked about how do we make ethers, so the question is asked, can that be both symmetrical and asymmetrical? And the answer is absolutely. It just really depends on what the original alkene is and what the alcohol is. They can be identical. In other words, here's an example of a situation where we could have one that's identical. So I could do that. And here would be my alcohol. And so I'm going to create a Markovnikov alcohol. Oops, that's not, here we go. And instead of a Markovnikov alcohol, it's going to be an ether. The question is, why would you want a symmetrical ether versus an unsymmetrical one, or does it matter? It doesn't matter from any particular reason why you would want one versus the other. If you're just creating something to use as a solvent, then a symmetrical ether works fine. And in fact, that's what we find as common solvents, is symmetrical ethers. But where it's important is from a synthetic standpoint when it comes to just problem solving, right? The Williamson Ether Synthesis is an important reaction in synthetic chemistry. So what you need to think about when it comes to symmetrical and unsymmetrical is that acid catalyzed formations of ethers from a particular alcohol will end up with a symmetrical ether. That's very easy from a synthetic standpoint, alcohol plus acid. But if I want to do Williamson ether synthesis to get an unsymmetrical, excuse me, senior moment, to get an unsymmetrical ether, then I have to use sodium hydride, and that's a little bit more aggressive of a reagent. So it doesn't matter, except if I'm going to give you a problem where I want you to synthesize an unsymmetrical ether. And so then you have to invoke one of the reactions that can do that. This one can do it as well as Williamson. So I could change this alcohol to be essentially anything I want. If it was this one, then I would end up with 3 carbon chain like that. So, yep, great. All right, so now we've talked about how to create ethers. Now we're moving on to the reactions of ethers. And so if I have an ether, I can react it with an acid halide, and I can create 2 alkyl halides. So how does this work? Starts off with the protonation of the ether. And now I've got a good leaving group. Let's make this, I'm sorry, I forgot to add my prime. So that formed the first one. And now I essentially do the same thing again, where HX comes along, protonates the alcohol, making another good leaving group that the halogen can then attack again. And that forms the other alkyl halide. So it's a little bit, it's not too much more complicated of a reagent. But it is another unique mechanism that you have to know from this chapter. So this is the acidic cleavage of an ether with of a acid halide. The only exception to this particular reaction is if the R group is phenol. Notice that the two steps that form each of the acid halides are SN2 steps, loss of the leaving group at the same time as a nucleophilic attack. This location is a sp2 hybridized carbon, and that does not do SN2 reactions. So if this is the ether that involves a benzene ring, then I'll get the same protonation that happens. But now when X comes along, you see in this mechanism, I could have done either step first. I could have had the X attack the R prime first, or it could attack the R first. And in reality, both is happening at the same time. At the end of the reaction, I've completely reacted both R and R prime. And so I have both alkyl halides created. But in this case, all I can do is attack R. This one will not undergo the SN2 reaction. And so attacking that way leaves me with only these two products, one of which is phenol and the other is the alkyl halide. So this is the only difference. And it's just like before, right? We've got there is this thing that's going on with phenol. In the first case, phenoxide has resonance stabilization. That means I don't need as strong as a base to create the alkoxide from it. And the same, I've got also when it comes to when it comes to hydrolysis of ethers, I can't create or can't do an SN2 reaction at an sp2 hybridized carbon. And so I won't end up with two alkyl halides. One of the alkyl halides I'll end up with is going to be phenol. And so that's just another exception, although it's similar. Does anybody have any questions about that? Pause just for a beat. Okay, so let's try this out real quick. What are the products of that reaction? How about this one? So just think about it just for a second. Think about how these reactions work. In the first case, they're both the same structure on both sides. And so I'm going to get a protonation here and the attack of Br at this location and at that location. So I'll end up with 2 of those. There's a little bit different situation happening here. And so I just want to show what's going on with this one. And I want to use the mechanism for that. So remember that I'm going to protonate the alcohol first. And now iodine can come along and do nucleophilic attack. Which one of these sites is it likely to attack first? If I were to ask you to do the mechanism, I'd want you to show me that it's going to attack the least substituted site first. Pencil battery running low. Okay, so notice that the stereochemistry hasn't changed with respect to the groups that were attached to the left of the hydroxyl group. Now the HI can come along and reprotonate this alcohol. Oops, look what I did. There we go. And I get this step is definitely going to be slower because of the steric hindrance in that location. But what's important about this particular reaction is that I'm reminding you that it is SN2, and even if it's slow, I'm going to form the stereochemistry of the SN2 reaction is maintained. So what happens here? So don't forget that there's an inversion in the stereo center, with this one being away from you. So I know that there's a lot that's going on here. You've learned a new reaction, you learned a new mechanism, you had to recall previous reaction mechanisms from Orgo 1, but not only did you have to recall previous reaction mechanisms for Orgo 1, you had to remember that there are certain stereochemical outcomes with those reactions. And so not only do you have to know the reactions and the mechanisms, but you have to remember that there's stereochemistry that's involved. Remember that the second step of the mechanism involves an SN2 reaction. So if there's an SN2 reaction, I'm going to end up with an inverted stereo center. One way that I can show an inverted stereo center is to change the position of the bonds, what's going forward, what's going backwards, or I can flip it over. And so I chose to flip it over in this case to show the mirror image. Does anybody have any questions? I want to just kind of pause there for a second and see if anybody has any questions. Give me a 1 in chat if you're overwhelmed, 2 if you're not. I see that. Shouldn't there be 2 iodines? Thank you. I totally didn't, like, I totally didn't. Someone's pointing out that, look, Eric, you didn't even finish drawing what's going on over here, right? I just left it off completely. And so let me add it on. 1, 2, 3, 4, and an iodine. 1, 2, 3, 4, and an iodine. 1, 2, 3, 4, and an iodine. Absolutely, that's still there. All right. Yeah. So what happened to the rest of it? I just forgot. I got excited about inversions in stereochemistry and I forgot. So that's what's good about you guys being live. So it looks like everybody is either overwhelmed or sort of in the middle. I don't see anybody telling me that they're, even privately, I don't see anyone telling me, hey, I'm okay with all this. And so that's not that. So look at all of you guys that are feeling the same way. So don't feel like you're alone when it comes to struggling with organic chemistry, especially organic chemistry 2. Remember that some of the stuff that a lot of the things that we're going to work on are going to recall aspects of Orgo 1 that you need to know. And so far today, what we've really recalled that is important is the reaction mechanism of the SN2 reaction. That involves some considerations about steric hindrance, but it also involved some considerations about stereochemical outcomes, namely that there's an inversion in the stereo center. And so it's important to go back and make sure that you have a complete understanding of what's going on from last semester. So someone says, can you explain the inversion again? And you just flipped it. Does that work to show the inversion? Yeah. Remember, if I have a stereo center like this, then the mirror image looks like this. If this is A, B, C, D, this is still A, B, C, D. They're still the same. They're still on the same types of bonds, wedges versus dashes. They're just reversed, the mirror image. Another way to show you the enantiomer is to take any of the two bonds, D and A, and switch them. So that means this one is still B and C. Or I could have done this. I could have left this one as A and D, but I could have also then switched this one to C and B. This is the original molecule. All of these are the enantiomers, and they're just different ways of showing it. Hope that helps. Okay. All right, so also from organic chemistry 2, what I want you to recall is this reaction. It's when I have a alkene and I react it with a peroxy acid. And actually, so this would be RCO3H. I would normally do it in one step, but then I would show something else going on. But I think if you remember, especially if you were in chemistry from last semester, I specifically made it a point to say that when I react alkene with a peroxy acid, that what I get at the end of the day, before I do any other reactions, is I get an epoxide. And so this is an epoxide. It's a 3-membered ring, and with one of the members being an oxygen. So if I were to have something like this, then I could name this way. We would still number it in the direction that gets us to the priority functional group. The priority functional group is the oxygen. So this would be (5-methyl) and the epoxy happens between the 2 and 3rd carbon. So it would be 2,3 epoxy heptane. I'm sorry. So the question was, what does this black dot represent? It's just a really messy oxygen. Clear that up for you? Yeah, relatable. I get it. Just going fast with my Apple Pencil here. So I wanted to make sure that two things, that I reminded you of this reaction of alkenes when it comes to its reaction with peroxy acids, that when we react an alkene with a peroxy acid, that we get epoxide. But then I'm also introducing the nomenclature. Why doesn't the epoxy come first in the name? Because it's like, the question's asked, why doesn't epoxy come first in the name? Because it's part of the parent. Since it's an epoxide, it's not really a substituent. It's actually like the parent of the molecule. So it's an epoxy heptane is the actual molecule. It's not heptane with an epoxy substituent, then you alphabetize. It's an epoxy heptane that has a methyl substituent. Does that answer your question? Yeah, great. Okay, and so there's just a couple of things that I want to remind you about when it comes to these reactions. One of the things this could be is MCPBA, metachloro, let's see, make sure I say it right, metachloroperoxybenzoic acid. And so remember that I can show you the reagent two different ways. I can show you the reagent as RCO3H, or I could show you the reagent as MCPBA. RCO3H is just the generic peroxy acid. MCPBA is a specific peroxy acid, but a common reagent nonetheless. And so there is one other thing that I want to talk about before we move on to a different way to create epoxides, and that's with some stereochemistry. So if I take alkane and I think about this type of alkane, I have a cis alkane or I have a trans alkane, then it's important to think about the stereochemistry of the outcome. In this case, if I create an epoxide, and I'm going to show the epoxide in the plane, then the groups that start off on the same side end up on the same side. If I do the same thing with the trans alkane, then the groups that are trans from each other stay trans from each other. And so remember that when I create this epoxide, even though this is a 3-membered ring, each one of these carbons is a chiral center, and so there is a stereochemical result that happens. And so this is going to be important when it comes to particular types of reactions. When you write the product, you have to consider whether or not the groups are cis or the groups are trans. Even if this group was not the same group, maybe we had to do ethyl here. then that just means that this group at the back becomes ethyl. And so it's important to show the correct stereochemistry. So the groups that are together will stay together when it comes to the epoxide. Now remember, this could form from above or below. So I also have this possibility. These are two different molecules. Just want to make sure we're okay with that. So plus enantiomer. All right. So let's see, where are we at? We got a couple more minutes left. So let's go ahead. Now that we've shown you a review from last semester, let's take another way to create epoxides. If I have an alkane or an alkene and I react it with Br2 and water, then I get halohydrin formation. So if I take that halohydrin though, and I react it with sodium hydroxide, then I can form an alkane. Or excuse me, then I can form an epoxide. And so the reaction that I want you to know looks like this. So it's alkene, step 1, Br2, water, step 2, sodium hydroxide, and then the result is epoxide. But this is another one where you should know the mechanism. And I'm going to start the mechanism here. And the reason I'm going to start here is because you should know the halohydrin formation mechanism from Orgo 1. If you don't, go back through the video content for Orgo 1, look for the video about halohydrin formation, and learn the mechanism that's step 1 that gets you to the halohydrin. It's a Markovnikov addition of OH with the Br adding on the other side of the double bond. But once I'm here, let's think about the chemistry that can happen. Hydroxide is a base. It can do a proton transfer from the OH group. It creates an alkoxide. And now the alkoxide does a type of internal SN2 reaction. And that's what creates ultimately the epoxide. Now, let's change this up just a little bit, and let's think about what happens if I start out with a ring instead. One of the things that you remember from the halohydrin formation reaction mechanism is that this happens with anti-addition. Briefly, a 3-membered bromonium ion forms in the intermediate, and when the OH adds, it has to attack from the other side. And so the OH and the bromine eventually end up on different sides of the ring, facing different directions. So it's anti-addition. And so if we think about that from the perspective of what if we had another substituent here? What if there was this? Then this thing would be out like this. And so when ultimately the alkoxide reacts, there are some implications for how the ring forms. So what I'm going to do is show this type of projection. So I've got the CH3 pointing this way and the epoxide pointing that way. So again, there are some stereochemical considerations to be made when it comes to forming epoxides, especially when we're dealing with rings. So I'm going to pause there and see if anybody has any questions. All right, so the reason why we're thinking about epoxides and we're spending so much time on epoxides is that when I think about a three-membered ring, there's lots of angle strain. Angle strain raises the energy of the reactant and ultimately makes it reactive. So if I take an epoxide and I react it with a nucleophile, then I can do a ring opening reaction where I create an alcohol with a nucleophile attached to it on the other end. And so these nucleophiles can be a variety of reagents. So what can the nucleophiles be? It could be sodium, excuse me. It can be a hydroxide salt. It can be a halide salt. It could be sodium cyanide. It could be a SH or an SR salt. It could also be a Grignard reagent. So Grignard reagents react with epoxides in a similar way that they do with carbonyl groups, but the result of the reaction is quite a bit different. For example, if I create an epoxide and I react it with methyl Grignard reagent, I still get an acid, but the OH forms at a different location than where the double bond forms. Or excuse me, I've said that completely wrong. The OH is located at a different place on the molecule than where the carbon-carbon bond forms. When we react it with a carbonyl group, the place where the carbon-carbon bond forms is the same carbon that is attached to the alcohol group. It could also be lithium aluminum hydride. That can also be the nucleophile. And in the case of lithium aluminum hydride, it's a type of reduction. And I end up with only an alcohol. There is a regioselective outcome that comes to all of these reactions. And so if I take one of these reactions, I take an epoxide, and I react it with, say, sodium cyanide, there is a particular regioselective outcome. The nucleophile adds on the side of the epoxide that is least hindered. And the reason really is quite simply a steric hindrance thing. In the reaction mechanism, I'm using the epoxide to the partially positive charge of the carbon on the epoxide to attract the nucleophile. So there's two spots that the nucleophile can be attracted to, there or there. And it is essentially an SN2 reaction at that time. So in this case, the mechanism is telling me, because it's essentially an SN2 reaction, the nucleophile adds at the least substituted location rather than the most substituted location. So I want to just stop there real quick, see if anybody has any questions, and I want to show you a quick example. So what if I take and I react it with what's the product of this reaction? Take just a second. See if you can think about that. Here's the nucleophile. It's a sulfide. So the nucleophile can add at this location or at this location. It's going to add at the least substituted location. So that means it's going to add on this side and not the right side because of the hydrogen providing a little bit less steric hindrance. At the same time, there's going to be an inversion of the stereocenter where on this side, the stereochemistry is retained. So again, it's not enough just to know the reaction. You really have to know the mechanism. And in the mechanism, that means that you have to consider possible stereochemical outcomes. I have inverted the stereochemistry here because this group is pointing up and now it's pointing down. So I have essentially reversed the stereochemistry there. Does anybody have any questions about this particular example? All right, what I'm going to do is I'm going to stop the recording right there.